you'll probably be really glad and relieved that we are at this lesson, because now you'll officially be able to use the rules for differentiation, the product rule, the power rule, the quotient rule that you recall from last year that until we've proven them with the limits, you really can't legally use them. But now that we have proven them, you'll be able to use them from this lesson forward. So that'll be really a relief for some of you, I think. So yeah, those are the things we're going to talk about. Power rule, product and quotient, how to take the derivative of negative powers, and then second, third, fourth, higher order derivatives. So just some of the basic rules we want to cover in terms of ground rules. Rule 1, if you start with a constant, then that derivative of the constant is always 0. The reason for that is because the slope of a constant function is 0, which is why the derivative is 0. Rule number 2, if you have the derivative of a constant times a variable, so c times u, where u is the variable, then the derivative will be c times the derivative of du dx. And so if the variable is just x, so we have that special case, d dx of cx, then the derivative of that would be the constant c times dx dx, which of course is 1, so the constant c. Visually, this is a linear function, and so the derivative, or the slope, of the linear function must be the value of the constant, which is the slope value. So that should make sense graphically to you as well. Leibniz helps us prove the power rule for derivatives, that the n value, which is the power, moves down to the front. So we see that multiplied out in front, and then we lower the power, or we subtract 1 from the exponent. So that works for any rational number. So it doesn't just have to be an integer, but it works for fractions as well. You just subtract 1 from the value of the fraction. It also works for irrational numbers. So if the power was rad 2, you would move rad 2 to the front and you would subtract 1. It works for e, it works for pi. Any irrational number, we can apply this power rule for derivatives as well. Rule number 4, all derivatives can be added and subtracted from each other as long as the derivative itself, or the original function, is differentiable. That means it's continuous with no corners, no cusps, and no vertical tangents. Then you're allowed to add and subtract at will. Okay, so if we're looking for a tangent line, remember when we're finding a tangent line, we need a point and we need a slope. So the point is given to us to be 1, 1. That's right here on the graph. And now we want the slope. The slope will be dy dx, which is the derivative of the equation x to the negative 1. So we want to take the derivative of x to the negative 1, which means we move negative 1 to the front, and then we subtract and we get x to the negative 2. So we have the quantity negative 1 over x squared is the value of the slope. The expression for the slope. The value of the slope then would be negative 1 over the 0.1 squared, so negative 1. So our tangent line is going to be y minus 1 equals the slope of negative 1 times x minus 1. And that gives us the negative tangent line, which skims off that point, just intersecting the graph once. So that's tangent, not tangent meaning like sine, cosine tangent, tangent being the geometry term that intersects a curve with one common point and a shared slope at that point. We can use derivatives to help us answer the question about horizontal tangents. So does the curve have horizontal tangents? This horizontal tangents occur by definition when the slope is 0. And so if you understand that definition, so they occur when dy dx is 0. So we want to find our dy dx, and set it equal to 0 to solve for where those points would happen. So that would be 4x to the third minus 16x plus 0, which factors into 4x times x squared minus 4, which factors into 4x times x plus or minus 2. So when we set this equal to 0, then we get 3 values for x. We get 0 and we get plus or minus 2. So this curve will have 3 different horizontal tangents. These horizontal tangents are occurring at these 3 positions on the graph. And so it'll be occurring at 0, 2, which is the y-intercept. It'll be occurring at -2, and then you want to find the y value for that. So looking back at the original equation, that would be 1632 plus 2. So let's see, -14. And then by symmetry, our other point is going to be +2 and also -14. So those are the 3 points at which horizontal tangents will occur. Now we get into sum and we get into products. We've done sum and differences, but now we have the products. And so if we have the product rule, u and v, then the product rule can be each function times the derivative of the other. So first we have u times the derivative of v dx, followed by v times the derivative of du dx. The order in the product rule is not important. You could start with v and then have du dx and then add to it x times dv dx. Okay. Either of those is fine. You can prove that again with Leibniz or Newton, actually. Either will prove the product rule. Sometimes you'll see this as b times a prime plus a times b prime. Okay, so the product rule is helpful in helping us find the derivative in a multiplication setting, so we don't have to FOIL everything out. You could FOIL these 2 binomials out and then take the derivative, but you might find it easier to employ the product rule. And so this would be quantity A, and this would be quantity B. And so f prime, I like to start with B, with the second one. So x squared plus 3 times 3x squared, which is the derivative of a, plus, and then x cubed minus 4, and then the derivative of b, which is 2x. Now you want to distribute and simplify, so we'll have 3x to the 4th plus 9x squared, and then plus distributing 2x to the 4th minus 8x. So overall, looking like 5x to the 4th plus 9x squared minus 8x is the derivative using the product rule. And from there, then you could answer any other questions that might follow after that. All right, the quotient rule has some similar, similar rhythms to it as the product rule, but the order for sure is key. And that is that you start with v being the function that is in the denominator. Make sure you always start with that first and then subtract. So you might also see this as b times a prime minus a times b prime all over b squared. So last year we learned low, 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 d high, right? So we always start with the low first. So low, 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 d high, minus high, d low, and then you subtract over the b squared. So order super important in this one. All right, so if we're looking for the derivative here, we're going to identify our b function as the denominator. So my f prime would be the quantity x squared plus 3, and then multiplied by 3x squared, so the derivative of the a term, and then subtract the a term, x cubed minus 4, times 2x. And the whole quantity then would be over x squared plus 3 quantity squared. Now it is usually customary to simplify the numerator, but you don't usually need to expand out the denominator. So as we simplify the numerator, we're looking at 3x to the fourth plus 9x squared, and then minus 2x to the fourth plus 8x, and the whole thing still over that denominator, x squared plus 3. So x to the fourth plus 9x squared plus 8x over the denominator in factored form. Now we can use our derivative rules to apply repeated derivatives. We can do the second derivative, we can do the third derivative. We've got these derivatives expanding over and over again. And so we'll learn what those mean, or, remember talking about concavity and some of these other things. But for right now, we're just knowing that we can take derivatives repeatedly. And see the notation. Newton is the one who uses the prime notation, whereas Leibniz is more common to use the d dx notation. And so if we're looking at this derivative, we would see how many derivatives we can take. The first derivative, dy dx, would be 4x to the third plus 4x minus 3/4. The second derivative, the notation, remember the 2 goes after the d, and then the dx squared. Another way to write that is d2 over dx2 of y. That would be the same thing, the second derivative with respect to x of the original function y. So the second derivative would be 12x squared plus 4. Third derivative with respect to x. In other words, the derivative with respect to x of the original y function. So that would be 24x. And then we can go as far as taking the fourth derivative, which would be 24. And then we run out of steam that the fifth derivative and all following derivatives after that would be 0. And so we've evaluated all possible derivatives and all possible orders of derivatives. All right, there you go. So we got that in under 15 minutes. So this should be just a chance for you to practice and brush up on those rules, rules that you'll use over and over and over again throughout the remainder of the year.